Good evening. Today we will discuss regarding the gravity separation process. I will wait few minutes more for people to join for today's class. In the last two classes we have discussed about the filtration process. Filtration process where we discussed about a solid to liquid separation process. So here in the gravity separation process, which will be focusing on the sedimentation process basically. So here we can also do liquid to solid separation method. This kind of applications, this kind of procedure is mostly applicable in wastewater treatment or waste handling plants or any kind of uh, like density based separation processes that we can go for industrial applications. It has and Mostly it has applications in the mineral processing industries, so we can discuss one by one. What we are going to discuss today, that is the gravity separation process, which generally separates two components, either a suspension form or dry granular mixture. So where we are separating the component based on the gravity. So here the main role that is playing, that is the gravitational force, which is which is playing a major role in separating mixture of component or having different specific weight. So all the gravitational method that we know, basically um, basically they work as a this kind of common applications, like gravitational force work on different specific weight mixture particles, and there the gravitational force is the dominant force. Now the gravity methods of separations are used to treat a great variety of material. Now this kind of material can be, we can have ore, we can have different kinds of mineral ores, we can have coal, huge applications it has. We are in other things like waste stream, any kind of waste stream, liquid streams, plastic waste. So this kind of waste separations we can also apply these gravitational methods. Now gravity concentration is more specific to separate the minerals of different specific gravity by their relative movement in the inside the medium in response to the gravity and um, in the presence of one another in the mixture of particles. So here when they are in the fluid like water or air, then they feel some resistance in the motion by either by any viscous fluid presence. So there the gravity concentration methods plays a great role in dividing or sorting out into fractions of that mixture of particles. So it is very essential to have very effective and clear cut separations of those mixture of particles, and so that it will be very helpful for us to go for gravitational methods, this kind of sedimentation separation, if they have the marked density difference. If the particles are uh, in the range of near uh, in the range of near gravitational, near a specific gravity, then it will be difficult to separate such in such method. So for that case we have to change the medium, that fluid medium specific gravity, by different methods that we will discuss. So another concept here, that is the concentration criteria. So here the concentration criteria is being defined as Sg, which is the specific gravity of the heavy material minus the specific gravity of the fluid or the medium, and a specific gravity of the light material minus a specific gravity of the fluid. So here what we can see that in a mixture of particles there will be certain particles which is having very higher specific gravity, or you can say higher specific weight. So by selection of that specific gravity of the intermediate fluid medium, we can set the concentration criteria accordingly. Now the thing is, when the concentration criteria, this value is greater than 2.5, either it can be positive or negative, that doesn't matter, but if the value is 2.5 greater than, then the specific gravity will be relatively easy. The specific gravitational separation will be relatively easy. Now the efficiency of the separation by such process decreases as the value of this Cc or concentration criterion will decrease. So this is a very important factor for when you are handling the minerals. So where the ore processing, in the ore processing industry, we will have the main mineral, which is having a separate specific weight, and the impurities, it has some separate specific weight. So we have to extract this mineral from these impurities. So it has different specific gravities, so we can do this gravitational separation method to to just take out minerals from this ore mixture. So this is one of the example that related to the mineral processing industry. So next one we are going to discuss about the classifiers, that is gravity classifiers. So the motion of the particle in any fluid medium is highly dependent not only the specific gravity, also also on its size. So the most important thing that we're going to focus on today's class, that is this particle having specific gravity as well as size. So we will focus these two cases simultaneously, or one keeping one constant and focusing on other thing, because there will be some cases when the two particles are near specific gravity but size is different, or there will be some cases where the particle having size is same but specific gravity is different. So the motion of the particles in the fluid will obviously depend on both of them. The larger particles will be affected more than the smaller particles. Now, gravity sedimentations, like in classifiers, what happens? It separates the particles into two fractions. These are the devices where the separate particles of different densities or specific gravities are treated, and they are sorted into different fractions. That's why it is known as sorting classifiers. So, in other words, separation of particles into different several fractions based upon their settling velocity is known as classification, and equipment is used as classifier. So, there are some commonly used uh, principles, principal methods for this classifier, gravity classifiers. Very known two methods that you all know maybe, that is the sink and float settling, and another one is the differential settling. So there are many classifiers in the chemical processing industry. Those classifiers separate particles based on their sizes, and especially when the density of the different types of particles are in the same range. So the efficiency of gravity processes therefore increases with particle size, and the particles should be sufficiently larger or coarser to move in accordance with the Newton's law. The particles which are very small, that their movement is mostly dominated by the surface friction, respond relatively poorly to commercially high capacity gravity methods. So, in practice, close size control of the feeds to the gravity processes is required in order to reduce the size effects and make the relative motion of the particles very dependent on the specific gravity. Now, these mechanical classifiers are used in the closed circuit grinding, especially in metallurgical operations that I told about the mineral and metallurgical operation. Now we are going to discuss the first methods for gravity classifier, that is the sink and float method. So this sink and float method, that is very usual, that you know that the particles of lower specific gravity, they will float on the surface of the medium, while the particles of higher specific gravity, they will sink down to the bottom. The two types of particles are removed separately from each other by the use of that medium, and a separation of the particles achieved according to the individual specific gravities of those particles. Now, a liquid of intermediate density it's required to be chosen such that the lighter material will float in that liquid medium and the heavier material will settle down in the liquid medium. So uh, we need to choose this solution specific gravity based upon our other two material specific gravities, so that we can efficiently separate these light and heavier particles. So this method is independent of the size of the particles and completely dependent on the densities of the material. So for this method, liquids must have densities greater than water, since most solids have very high densities. But unfortunately, there are few such liquids exist that are economical and non-corrosive. So we are making some pseudo liquid or synthesized liquids according to our desire, and how we make such kind of um, densities of the solution medium by adding very fine solid materials with very high specific gravity such as galena and magnetite. So here most of the case when we handle the sink and float method, here mostly the hindered settling situation appears and bulk of density of the medium can be tuned or varied widely by varying the amount of the fine particles that we are adding in the medium to determine the specific gravity of that fluid medium. Now for the very fine solid materials in the medium, they are considered to be very small in diameter, that their settling velocity is very negligible. They give a very stable suspension. Example, concentrating the ore materials and cleaning the coal is such an option. So here we can see a system or arrangement for sink and float method. Here the feed is introduced and it maintains a level in the float and sink container or the system. Here the skimmer that carries out the lower density material to the top and it carries out from this end. And this solution can be saline or water with some nano size material, very fine material, so that the specific gravity is maintained. So the specific gravity of the liquid should be in between of these two the specific gravities of those material. And the higher density particles will be collected from the bottom end of the system. So in the next process, that is the differential settling method, we can have these two material from where we will compare that at in which range this settling method can be effective, and we will operate the particle size of the feed in that range so that there will be clear cut separation between particle A and particle B. So this differential settling method, they uses difference in the terminal velocities of different density materials. The density of the medium is less than that of either two substances to be separated. Now the thing, the when we operate this kind of thing, then we see certain problem that the mixture of materials to be separated, they generally cover a range of particle sizes. Now, if the situation occurs that the larger and lighter density particles, they settle down at the same settling rate as the smaller but heavier particle. So ultimately, when they settle down, settling velocity becomes equal, the ultimate fractions are not clearly sorted out. So there also we will get mixed fraction. Now the two materials that we are considering for this case, that is the material A and material B, where the material A is heavier and material B is lighter. We are considering the medium density as rho. The terminal velocity of any particle of size dp and density rho p we are considering and settling under gravity through the medium of density rho that is shown in the figure. So here we can see that mixed fraction can be reduced or eliminated if we are doing closer sizing of the feed. So here what is happening when we are increasing the particle size at a constant terminal velocity, here we got that at a constant terminal velocity, here we got that this for this reason all the particles of material B shows very slower settling velocity than the material A. So in this region we will get very clear cut sorting between material A and material B. Similarly, when you go up and the terminal velocity again increases, then you reach a point where the both terminal velocity you are equaling, but you will get that this range of particles of particle A who, uh, whose terminal settling velocity is uh, higher than the terminal settling velocity of the particle B at this point. So in this region also you will get a very faster settling differential settling velocity of all the size ranges of particle A than the particle B. So if you are feed material, you are choosing the feed size between this range or this range, you will get a very clear sorting between particle A and particle B. So now we are going to discuss about the equal settling particles. So these equal settling particles can have two different cases. One is the case where the particles having the same terminal velocities. So we know that for Newtonian regime, we get this terminal settling velocity definition as u equals to root over of 4 by 3 rho p minus rho f dp by cd as we have defined that not rho f, we can define as only rho, and we can write it down dp by cd into rho. So this is the general one. For particle A and particle B, we will get two different notation. Rho PA minus rho dPA CDA into rho. Similarly, for another particle, rho PB minus rho dPB divided by CDB into rho. So now we are having the case where they have the same terminal settling velocity. So if you equal these two, what will be the case? You will have the if you equal these two, you will have rho p minus rho into dPA divided by CDA into rho p b minus rho into dPb CDB into rho. Just we have done the equal. So ultimately we get a equation like dpa by dpb equals to rho pb minus rho pa minus rho cda and cdb. So when we are considering um, at a very high Newtonian flow regime, so in very high Reynolds condition for Newton's flow regime, we will get CD at a constant value 0.44 for spherical particles. So just replacing these two terms, we will get dPA dPb equals to only so this is the case for Newton's law regime. But for laminar flow regime, you have to uh, go for this CD equals to 24 mu by dp ut to rho. You have to replace this CD with this and you will get from there you will get this equation. So this is nothing but after solving you will get square square because these two terms are similar. So this will cancel out and you will get So this one is for laminar flow resin. So next, the other criteria that we are going to go for the equal settling particles in terms of particles having equal sizes. So in the case of the particles having equal sizes, so we again have the same formula for two different particles for Newton's law regime. So for equal sizes at high and high Reynolds number, these two are becomes equal. CDA CDB equals to 0.44 for high Reynolds number. So these two get cancelled and this particle size are getting equal. So for this case, the simple settling uh, ratio will be root over of rho PA minus rho and rho PB minus rho. So this one is having uh, Newtonian regime. So you have to understand, remember this one. This one is Newtonian regime. Similarly, the same thing when we follow for laminar flow regime. That ratio will become and also there will be certain terms. This thing you are utilizing because this CD is 24 by Reynolds number that we have replaced. So from that we got equals to the power 1.5 minus rho to the power zero point 0.5. So ultimately we got a value between, after solving this, one third. So this is the equation for a laminar zone. Now when you are going for any kind of transitional zone between these two Reynolds number zone, that is laminar flow and turbulent flow, you will have in between of this n value will have zero point 0.5 and 1 by third. This between this value you will get. Now we are going to discuss about the normal settling tank where the gravitational sedimentation is happening, which is also can be known as classifiers. So here slurry feeds enters into the tank of different chamber it has at certain inlet connect concentration. As soon as the slurry feed enter into the tank, its linear velocity decreases as a result of the enlargement in the cross-sectional area. So as soon as it enters, the linear velocity decreases, so it starts to settle down at the bottom of the tank near the inlet. And while the slower settling particles will be carried further into the tank before they reach to the bottom of the tank. So, in such way, the very fine particles will not settle down till it reaches to the end of the uh, settling tank, and and over the period, the fine particles will be collected from the fluid stream here. Now here we use the vertical baffles, which are being placed at a various distance from the inlet within the tank, which allows for the collection of several fractions according to the terminal falling velocities. Because of the occurrence of considerable overlapping of size, no sharp separation is possible with this kind of classifiers. So here we can see in the picture that slurry feed enters, and more the heavier and coarser particle, they will immediately settle down in the first chamber. The rest of the material will be carried forward to the next chamber, chamber 1, 2, 3, and here the intermediate particles are being collected. Similarly, the rest of the product goes to the fine particle, where the very fine materials are being collected because they have the longest route, because they have lesser tendency to settle down. So this uses the hydraulic classifier, where we are introducing the slurry into the system, and it consists of several conical vessels of increasing diameter in the direction of the flow. So this chamber is bigger than the rest of the channels. Now the thing is, the slurry enters the first vessel, where the most largest and fastest settling particles are immediately being separated. Then the overflow, it goes to the next vessel, where another separation occurs, and this gets continued to succeeding vessels. In each vessel, the velocity of the upflowing inlet water is controlled to give the desired size ranges of each vessel. So here we can see that at the first, the coarser solids are collected. In between, it is intermediate solid fractions, and at the last it will be fine solids. Now we will go to the portion where we will discuss the classifier and thickener. So, gravity separation, where it is happening under hindered settling method, because there is very less real examples where the free settling occurs over the period. So mostly there occurs hindered settling method. So it is often used to convert the dilute slurry of the fine particles into clarified liquid and a concentrated suspension. So this process is carried out in a large open tanks which is called thickener and clarifiers discharged as a waste. Now clarified liquid is free or nearly free of the solid particles, and it may be reused as a process water or discarded as waste. So this can be done by flocculation, batch or continuous sedimentation process. First one we will discuss about flocculation process. So flocculation process is where we want to make the bigger size of the particle and we want to make them settle down easily in the gravitational process. So if the subparticle size are already very small, only few microns in diameter, gravity settling rate will be very slower in practical suspension. So, however, in many cases, they automatically form agglomerate or clusters of particles which can settle down at a very quicker rate. Now the agglomeration can be promoted by adding flocculating agents to the suspensions. Now we add different kind of flocculating agents depending on the type of the particles which are present in the stream. Now this flocculating agent can be electrolytes which reduces the repulsive forces between the charged particles. Sometimes the polymeric flocculant can also be used using some cationic and anionic in nature. So some relatively economical flocculants such as lime, alumina or sodium silicates also we use to form loose agglomerates. Settling velocity of the flocculant can be very different from those of the dispersed dense solid. Now the final agglomerate have higher porosity, then that can retain considerably amount of water that accompanies flux while settling. So agglomerates are loosely bound and sludge at the bottom of the settler. They compress under weight of the additional solids over the period. Because of the size, shape and effective density of the flux, which are not readily definable, it is not possible to predict the settling rate and the sludge density from theoretical consideration. Now, design of the thickener is generally based on the measurements of the settling rates and which is being obtained from the batch test in the laboratory. Now we are going to discuss about the batch sedimentation process. So the equipment for batch sedimentation process is very simple, that is a cylindrical tank with opening for slurry feed and product draw off. Tank is filled with dilute slurry and you can see that at the initial the solids are high enough in the concentration that the sedimentation of the individual particles or the flux is hindered by the presence of each other, and here the initial and they all settle at a common velocity at the very first, and when it is uniformly distributed in the liquid the depth of the suspension was z0, and after a certain time the zone A, which is the clarified liquid uh, depth, and the zone D, which is the bottom one, that one is the settled solid. Zone A is clarified liquid and zone D is settled solid. So here the zone C, when it comes, it becomes the transition point where the concentration of the solid is different uh, from that section D, or the initial concentration of the solid in the solution. So there are some boundaries between the zone D and zone C, and between zone C and zone B may not be very distinct. Boundaries between zone A and zone D, obviously it is quite visible, and it increases. That of C remains constant and that of B remains, it starts decreasing over the period. So eventually what happens, that um, the zone B disappears and all of the solid of the zone C comes to the zone D. So at the last we see clarified water and all the solids compacted at the bottom of the container, that is known as compressed solids. So finally, when weight of the solid is balanced by compressive strength of the flux, sedimentation process stops. So this is a flocculated suspension process. So here we over the period we separate the solids from the liquid with clarified liquid, and we get the solid at the bottom of the tank. Now the rate of sedimentation that we get, that initially when it was initial, the clear liquid interface height was maximum, and over the period the final height got delayed. So at initial stage at settling velocity is constant. When the zone B starts disappearing, the rate of settling starts to decrease and steadily drops until the ultimate height is reached. While the settling slurries vary vary greatly in their settling rates and in relative heights of various zones. So, initial rate is the function of feed concentration, but in the last stage, settling rate also depends on the initial height Z0, since compression effects are more important with the thickener sludge layer. There are experimental studies of settling rate of different initial heights and concentrations are needed for design of a thickener. So the design of a thickener we will discuss in the next class. So now we are going to discuss about the last topic today. That one is continuous thickener. So this continuous thickener having very large diameter, you can see flocculants are added in the feed well. Slurry is fed also at the center of the tank and around the top edge of the tank is will be clear liquid. First one is the clarified zone, settling zone, hindered settling zone and compression zone at the bottom. So racks here serves to scrape the solid sludge towards the center so that we can collect the center sludge as underflow. Motion of the rack also stirs only the sludge layer. This gentle stirring aids the water removal from the sludge. In thickener, the entire slurry spreads radially through the cross section of the thickener and the liquid flows upward and overflow is collected. So the solid settles down over the period by free settling. Below this dilute settling zone, there is transitional settling where the concentration of the solids increases rapidly and then compression zone. A clear overflow can be obtained if the upward velocity of the fluid in the outlet zone is lesser than the terminal velocity of the solids in the zone. Settling rates are quite slow in the thickened zone, which consists of a compression of solids with liquid being forced upward through the solid. So there was extremely hindered settling at the bottom part of the thickener, where over the period there is over concentration or um, height of the solids. So here in this region the hindered settling velocity achieved, but in above there is free settling velocity. So this design of the thickener will be discussed in the next class. So for this class we will solve one numerical. So these numericals shows separation of mixture of silica and galena. They have particle size ranges from this to this meter, is separated by hydraulic classification using free settling condition in the water at this Kelvin. So the specific gravity of the silica and galena is mentioned. You have to calculate the size range of various fractions obtained in that hydraulic settling. If the settling is occurring in the laminar region, the drag coefficient will be reasonably close to that of the sphere. So for this, you have to solve this question. I will write down the data that has been given. So here water is row of water is viscosity of water. So following the laminar region, you can have the terminal settling velocity as it has been told that you have to consider, you have to check if that is in the laminar region. So we will calculate first the terminal settling velocity. Then we will check that if it is laminar region or not. If you do this equation for particle A, so what will be the value? So this value becomes 2.203 into 10 to the power minus 3 meter per second. Now you got this value. So what will be the Reynolds number for this case? We can quickly calculate. So this value becomes 0.0547, which is obviously laminar. So we have checked it and we will go forward with the calculation. Now what we have, that we already have confirmed that this is the Stokes law regime. Now we will go for the largest particle. Um Largest particle we have calculated. Now we will go for the smallest particle. The smallest size is dp1, right, which is 5.21 into 10 to the power minus 6 meter. So the pure fraction of A, which consists of dp4 and dp4 to dp3, where we already know these values dp1 and dp4. So we need to calculate the value of dpa3 and dpb4, because they have the related to equal settling velocities. Equal settling velocities. Following to the laminar regime, we get dpa3 4 equals to from here this value is same as dp4, is also 5. This largest one 2.5 into 10 to the power minus 5 meter. So from here dpa3 will be calculated as 1.0 into 10 to the power minus 5 meter. Similarly, in this size range, dp2 and um, dpb2 and dpa1 having the similar mm, settling velocities. So for them we can calculate So these are the thing. So what we have got, that mixed fraction for pure A, we have the pure A have dp3, dp4, these two fractions we calculated, we got to know. So pure A will be in this region, whereas pure B will be in the region of these two, that is. And the mixture of particles will be dpb2. So these are the fractions obtained we have calculated. So in this class we will end after this session, after this point. So I hope this is clear, like this equal settling particles, the concept is being used in this calculation for this numerical, and this is very straightforward, and we have calculated the pure A and pure B and mixture of fractions, um, all the size ranges. So I will end the class here today. We will discuss more about the design part of the thickener in the next class.